Just give me a second. Okay, yeah, let's start. So this subject, discrete mathematics, this is a very important subject from the computer science point of view, or you can say from the gate point of view. So first let's see how much is the weightage of this subject. So in the gate exam, almost you can say almost 8 marks. So you can say that from 7 to 9, this is the weightage of this subject. But actually, the beauty of this subject is that it is used in all other subjects. Like in this subject we study counting, we study graph theory, we study mathematical logic, first order logic, quantifiers, okay, set theory, set relation functions. So many concepts, many concepts that we study in this subject. All those subjects, all those concepts we use in other subjects, whatever subject you can take. For example, if you take algorithm or data structure, then there we use the concepts of graph theory. You can see many times we study graph algorithms, minimum spanning tree, okay, or you can say Dijkstra algorithm. So many graph algorithms we study, so there we use the concepts of graph theory. Similarly, you can see like we use the concepts of counting in all other subjects. We count the number of like how many are the schedules in transactions. We in dbms we find number of schedules. Okay, whatever subject you take, we use counting, and we basically find like how many number of some things are there. So these type of things. And this set theory, like what is a set. So the concepts of set theory, union, intersection, complement, okay, universal set. So these concepts of set theory we use in all other subject. So that is the you can say importance of this subject. If you are good at this subject, then basically all these basic concepts you already know. Okay, so that's why you must be good at this subject, and this is a mathematical subject. So you need to practice. Whatever mathematical subject you can take, you need to practice a lot. Okay, so that is the importance of this subject in the gate exam. This is the weightage of this subject, and you can see in all other subjects we will use it. Okay, now in this subject, basically we can divide this subject into some modules. For example, we can say that mathematical logic, this is a module. Okay, similarly we can say that set theory. Okay, next after that we can say group theory. Okay, next we can say graph theory, and we can say combinatorics. So these are the modules. We can divide this discrete mathematics subject into these 5 big modules. Okay, each module is important. And actually from in the gate exam, you will see that from each module you will get at least one question. You will get at least one question from logic, one question from at least one question from set theory, at least one question from group theory, at least one question from graph theory and combinatorics. So that is the beauty of this subject. The marks distribution is uniform. Okay, you will definitely get one questions from each subject. Okay, so so that's why that's what makes each topic, each module very important. Okay, so you should not leave anything. Many easy questions are also asked in the gate exam from some topics, like from group theory. Mostly from the group theory they ask very easy questions. Most of the time they ask questions from the Lagrange theorem and these kind of things. So today we will discuss mathematical logic, and first we will see the first we will revise the mathematical logic, and we will see the basic concepts of mathematical logic. And then we will see some tricky questions, some questions like you can see if you have solved the previous year gate questions, then you have seen some model based questions. Okay, like is there a model of universe of size 3? So there is a question in 2018. Okay, there is a model based question in 2018. In gate 1991 there is a model based questions. Okay, so these tricky questions we will try to solve in today's session. Okay, so let's start. And of course, at any point of time, if you have any doubt, then you can ask in the comment box. I'm looking at the comment box also, and I will answer your doubt. Okay, so let's start. In first we will see what is mathematical logic. In this mathematical logic, mainly in our gate syllabus we have two type of logic. So first of all, the first module that we have is mathematical logic. Okay, in this mathematical logic mainly we have two topics, two type of logic we study, or we can say that in gate syllabus we have two type of logic. One is propositional logic, okay, and another is first order logic. So these are the two type of logic that we have in gate exam. Of course there are different type of logics also. Okay, first propositional logic, first order logic, second order logic, third order logic. So there are many different type of logics, but in gate syllabus we only have propositional logic and first order logic. These two things you have. Okay, this first order logic, this is also called predicate logic. Okay, so basically in our gate syllabus we have propositional logic and also predicate logic. These two topics we have. This propositional logic is very easy. This is basically similar to the Boolean algebra. In digital logic subject, you have a topic called Boolean algebra. So this propositional logic is actually isomorphic to Boolean algebra. They are very similar. Okay, we will see how much they are similar. Exactly similar they are. Okay, so that's why we call them isomorphic. This Boolean algebra is isomorphic to propositional logic. If you understand Boolean algebra, then you can very easily understand propositional logic. If you understand propositional logic, then very easily you can understand Boolean algebra. Okay. Now the important, or you can say uh, more like harder than propositional logic, that is first order logic. In this first order logic, we have some concepts which are tricky concepts. So we must take utmost care when we are solving questions from first order logic. Okay. Now, so first let's see what is this propositional logic. In this propositional logic, basically remember that I am not teaching the complete subject. I am just quickly I am doing the revision of this subject. I am going to go through over all the concepts. Okay, so like in propositional logic, the first thing that we study is what is a proposition. So this proposition is nothing but a statement. This is a declarative sentence which is either true or it is false. For example, you can say that this statement, let's assume that we have this statement like Delhi is the capital of India. Okay, Delhi is capital of India. So we can say that this is a Delhi is capital of India. This is a declarative sentence. Okay. So because this is a declarative sentence and you can see either this is true or this is false. We know that this is true. But the point is that either this is true or this is false. So this is a proposition. So every proposition, this is a proposition, and every proposition is either true or it is false. Okay. Now actually we don't want to write these long sentences every time. So what we do, we represent this proposition using a variable. So let's use a variable p. So this is a variable which is representing this proposition. So that's why this is called propositional variable. So this p is a propositional variable. Okay, and remember this p is representing this proposition. So the truth value of p is either true or false. So again, this p is also either true or it is false. So this true or this is false, this is called the truth value of a proposition. Or you can say this is the truth value of a propositional variable. For example, if you have a variable, let's assume there is a propositional variable p and this is true. Let's assume there is another propositional variable q. This is false. Then what we say? We say that truth value of p is true and truth value of q is false. Okay, so this is our propositional variable, this is proposition, and this is the truth value of a proposition, or you can say truth value of propositional variable. Now what we do, sometimes what we have simple propositions. For example, p is a proposition, q is a proposition. So this is a proposition, this is a proposition. And now what we do, we can construct more propositions. Okay, using these propositions we can construct some new proposition. For example, we can construct a proposition like p and q. Let's assume that this p is basically Delhi is the capital of India. So you can see the truth value of P is true. We know that that proposition is true. Similarly, let's assume that this Q is Kolkata. Kolkata is the capital of Maharashtra. Now, the truth value of this Q is basically false, because the proposition, this propositional variable, this is representing the proposition that Kolkata is the capital of Maharashtra. Now, this is a false proposition, so the truth value of Q is false. But what we can do, we can construct new propositions from this P comma Q. For example, we can construct a new proposition R. So this R is a new proposition which is P and Q. So what is this? This is basically Delhi is the capital of India and Kolkata is the capital of Maharashtra. So you can see that this is a new proposition. So this is called connective. This is called connective because this is connecting two different propositions and finally it is giving us a new proposition. So that's why this is called connective. Okay. Now in propositional logic, we have some connectives, some set of connectives we have. Okay, like we have negation, we have conjunction, we have disjunction, we have implication, we have by implication, we have XOR, we have NAND, we have NOR. So this is the set of connectives that we have in propositional logic. Okay, so like this and is our conjunction. Okay, and and some other connectives we have. Okay, and each connective has its own definition. Each connective has its own definition. Okay, and that definition we represent by truth table. So truth table is one of the way to represent the definition of a connective. So let's see the definition of each connective. So the definition of each connective you can find in this truth table. So let's see the definition of each connective. Let's assume that P is a propositional variable, Q is a propositional variable. Now let's see the definition of each connective, or you can say the behavior of each connective. So this is P, this is Q. Now what we do, you can see that this P is a propositional variable, so this either can be true or this can be false. Similarly, this Q is propositional variable, so this either can be true or this can be false. So how many different possibilities you have? Total 4 possibility, because this P has 2 possibility and this Q has 2 possibility. So total 4 possibility we have, like false false, false true, true false, and true true. These are the different possibilities that we have for P comma Q. Now let's see the definition of negation. The definition, or you can say the behavior of negation. Like let's find out the negation P. What is negation P? This is simply like if P is false, then negation P will be true. If P is false, then negation P will be true. If P is true, then negation P will be false. If P is true, then negation P will be false. So this is the definition, or you can say this is the behavior of negation. Now let's see the definition of conjunction. This is your conjunction. This is also called AND. So basically this is P and Q, and the another name for this is conjunction. Okay, and remember this is your negation. So this is negation P and this is P conjunction Q, or you can say P and Q. Now what is the definition of this conjunction connective? The definition is very simple. It is false when at least one is false. At least one of them is false. For example, here both are false, so this is false. Here at least one of them is false, so this is false. Here at least one of them is false, so this is false. Here both are true, then this is true. So this is the definition, or you can say this is the behavior of conjunction. Now quickly we can see the behavior of disjunction. This is disjunction, and the behavior is basically this is false when both are false. In all other cases, basically when at least one of P comma Q is true, then this will be true. So this is true true true. So this is the definition or behavior of disjunction. So this is called disjunction. This is your disjunction. This is also called OR. Okay. Now let's see the next connective, and the next connective is implication. P implication Q. This implication is a very important connective in our mathematical logic. Okay, this is a very important actually, like in computer science, this is a very important connective. So right now we will not discuss it in detailed manner. but this is an important concept and you should know this concept. But let's see the definition, the behavior of this implication. This implication basically says that if P is true, then Q should be true. Remember, if P is true, let's assume P is true. Now, Q should definitely be true. So this is the definition of implication. Remember, this implication tells us what will happen when P is true. Okay, so you can see that this implication tells us what will happen when P is true. But remember, this implication does not tell us what will happen when P is false. So this basically says that if P is true, then Q must be true. Now, what will happen if P is false? Then this Q can be true or this Q can be false. So that's why the definition of P implication Q, this will be basically, you can see when P is true, then Q should be true. So in this case, this is true. When P is true, then Q should be true. But here you can see P is true, but Q is not true. So in this case, implication will become false. But remember, if P is false, then Q can be true or Q can be false. Okay, when P is false, then Q can be true or Q can be false. Hence, you can say that this is true, true, false, true. So this is the behavior of implication. Anil is asking, sir, why not false? Anil, I did not get your doubt. In which part you are asking? Let me know. So, okay, you let me know where are you having doubt. Okay. So this is the definition of implication, and this is the most tricky concept, or you can say this is the most important concept from the gate point of view. So you can see that this implication is always true. Okay, this P implication Q, this is always true, except in one case. This is the only case. This is the only case in which this P implication Q is false. Means when P is true and Q is false. In this case, this P implication Q will become false. In all other cases, this implication will become true. Okay. So, okay. In implication, in implication you are asking. See the definition, this is how implication has been defined. Remember, this is the definition of implication. Okay. So actually what some people do, let me tell you, what some people do, they first make the intuition and then they make the definition. But actually this is not a correct way. Okay, remember, first we should know the definition, how something has been defined, then we should build intuition, how to remember. Like once we know the definition, then we can build intuition so that we can remember that definition. Okay, similarly in this implication, this is the definition of implication, this is how this implication has been defined. Okay, like this is basically false false, false true, true false, and true true. And this implication has been defined like this, that this implication will be false in this case, in all other cases this will be true. This is the definition of implication, this is how implication has been defined. Now, once we know the definition of implication, now we can build intuition. How to remember this definition? Okay. So very easily you can remember this definition. This definition basically is like this. P implies Q. Means if P is true, then Q should be true. But remember, if P is false, then we are not saying anything about Q. Okay. For example, you can say that every person here is intelligent. Okay, I can say, I consider this statement. I am making a statement. I am making a statement that if a person is here, by here I mean in this YouTube right now, we are 24 people in this YouTube live. Okay, so if a person is here, then he or she is intelligent. So you can see that. So this is a statement. Now this is a true statement that if a person is here right now in these 23 people in this YouTube live, okay, then he or she is intelligent. But remember, we are only making the claim about those students which are here. Okay, for those students which are here, I am making the claim that they are intelligent. But remember, I am not saying that if someone is not here, then he is not intelligent. I am not saying that. So basically, what I'm saying, I am saying that if P is true, means if you are here, then you are intelligent. So if P is true, then Q is true. But remember, if P is false, means let's assume someone is not here. Okay, like Einstein. Okay, or you can say Elon Musk. They are not here. But I'm not saying that they are not intelligent. So if someone is not here, if this P is false, then this Q can be true or this Q can be false. We don't care about the truth value of Q. So that is the behavior of implication. Once this condition becomes false, this is the condition. Remember, this is the condition. Like here we have put a condition that if a person is here, this is the condition. If a person is here, and this is the result, or you can say this is the conclusion. If a person is here, then he or she is intelligent. So this is the condition and this is the conclusion. Means if this condition is fulfilled, once you fulfill your promise, once you fulfill your condition, then you should definitely get the conclusion, you should definitely get the result. Okay, but remember, if you do not fulfill the condition, if you do not fulfill your promise, or you can say if you do not fulfill this condition, then we don't care about the result. Okay, so that is the point, and this is how you can remember, like this is the intuition behind implication. Okay, but remember, this is only intuition. Okay, sometimes this implication, when we are studying in this uh, like in mathematics, remember, common sense, let me tell you, I will give you many examples where this common sense is basically the, you can say, worst thing that you can have in mathematics. In mathematics you should not have common sense. Okay, I will give you many examples why I am saying this. Okay, because this common sense will make many questions wrong. Okay, so for example, let me give you one example. If you make this statement, okay, I am making a statement that if you sleep for 2 years continuously, if you sleep for 2 years continuously, like a kumbhakaran, if you are sleeping for 2 years continuously, then you will get AIR1. Then you will get AIR1. So this is my claim. Okay, let's call it C. So this C is my claim. What is my claim? I am saying that if you sleep for 2 years continuously, then you will get AIR1 in GATE exam, in JEE exam, whatever exam, in UPSC exam. You can do, like in GATE exam, you can ask, you can say GATE exam. Now you can see that if you make this claim to anyone who does not know discrete mathematics, if you go to someone, okay, you go to your parents and you tell them that if I sleep for 2 years continuously, then I will get AIR1 in GATE exam, they are going to slap you, they are going to shout at you, because they are using common sense. From the common sense, this is a false statement, but from discrete mathematics point of view, this is a true statement. Okay, because why this is true, let me tell you why this is true. If you want to make this false, see, this is a implication statement. Basically, I am saying that this is your P, this is your P. So I am saying that P implies Q. So what is P? P is you sleep for 2 years continuously. This is P. And this is Q. You will get AIR1 in GATE exam. This is Q. So this, my claim is basically P implies Q. I am saying that if you sleep for 2 years continuously, then you will get AIR1 in GATE exam. Now this claim actually is true from the discrete mathematics point of view. This claim is true. Let's assume that someone comes to me and they tell me that this claim is false. What they have to do, if they want to prove me false, let's assume they want to prove me false, then what they will have to do, they will have to make it true, then make it false. So basically they will have to make it true and they will have to make it false. But the thing is, they cannot make it true. No one can, like, no one can sleep. Whoever will come to me, okay, someone will come to me, then I will tell them that this claim is true. They will tell me that this claim is not true. I will tell them, prove it. prove me false. Then what they will do? They will make P true and they will make Q false. But they cannot make P true because they cannot sleep for 2 years. So that's why this P is true. This P is false. This P is false. Hence, automatically this claim is true. So that's why in computer science or in mathematics, you should not use common sense. Like some many times this common sense will get you wrong. Okay. So many examples we will see. I am giving you one more statement. Okay. And at the end of this class, I will give you the proof why that statement is true. Okay, I am giving you one statement. Right now, you might be thinking that that statement is wrong. From the common sense, that statement is indeed wrong. But from mathematical point of view, from discrete mathematics point of view, or from gate exam point of view, that statement is true. So let me give you a statement, and this statement I am making it as, and this statement is that there exists someone someone here. By here I mean in this YouTube live right now 22 students, 23, 25 students are there. So there exists someone here such that such that if he or she is if he or she is a drinker, if he or she is drinker, then everyone is drinker. You can see. So this is my statement, this is my claim. Okay, or actually you don't have to put it here, you can put it in the world. In the world you can make this statement. So consider this statement, just consider this statement. I am saying that there exists someone in the world, in this universe, there exists someone in the world such that if he or she is drinker, then everyone is drinker. Now from the common sense point of view, this S is false. You can try it. You can go to anyone who does not know discrete mathematics. You can go to them and you can ask them whether this statement is true or false. They will immediately tell you that this is false. This statement as, this claim as, this is false. They will tell you because from common sense, this is false. Because indeed we have people who are drinker, but not everyone is drinker. So, but actually I will give you proof. I will give you proof, mathematical proof I will give you, correct proof I will give you, and I will prove it to you that this statement as actually is true. From discrete mathematics point of view, this statement as is true. Okay, so at the end of the class, we will see the proof of this statement. Today we will see the proof of this statement. Actually, this statement is true. In GATE exam, if they ask you this question, then this is actually true, and this is always true. Like you can say this is always true. This type of statements are always true. So we will see why they are always true. But anyway, the point is that this is how implication has been defined. So this is my point. This is the definition of implication. And I have also given you the intuition behind the definition of implication. Now we can see the definition of by implication. What is the definition of by implication? Very simple. By implication says that this by implication will be true when both P, Q have same truth value. What it means? It means when both are false, if like P is false, Q is false, both are false, then this will be true. It means basically when they have same truth value, they have always same truth value. Okay, like here you can see both are true, so this will be true. But you can see here one is true, one is false, so that's why this is false. Similarly here P is true, Q is false, so this is false. What it means? It means P by implication Q, this is true when both P, Q have same truth value. So this is the definition of by implication. This by implication basically tells us that P implies Q and Q implies P, both. This P implies Q and Q implies P. So this is the definition of by implication. What is the definition of XOR? The definition of XOR is very simple. This is basically complement of by implication. In by implication, we are saying that both P, Q should have same truth value. Then this by implication will be true. This XOR says that both must have different truth value. Then this will be true. For example, here both have different truth value, so this will be true. Here you can see both have different truth value, so this will be true. And here they have same truth value, so this will be false and this will be false. So this is the definition of XOR. Can you give please an example of by implication? Let's see one example of by implication. Okay. So one example of by implication, you can very easily see that uh, like, see, consider this statement: P implies Q. Let's call it G1. So this is our formula, P implies Q. And let's take G2, that is P dash plus Q. So this is your G2. Now I am saying that my claim is that G1 by implication G2, this is always true. This is always true. This is my claim. Let's prove it. We can prove it very easily. We can prove it. So what I will do, I will make the truth table. From the truth table, I am going to prove that this G1 by implication G2, this is always true. Let's see. So for example, this is P, this is Q. Now, okay, what are the different possibilities? Both can be false, this can be false, this can be true, this can be true, this can be false, and both can be true. Okay, these are the different possibilities. Now let's make truth table of P implies Q. What is the truth table of P implies Q? This we have already seen. This is basically true, true. In this case, when P is true, Q is false. In this case, this will become false. In all other cases, this will become true. Now let's make the truth table of P dash plus Q. What will be the truth table of P dash plus Q? Very easily you can make. First, let's make the P dash. What is P dash? P dash is basically, if P is false, then P dash will be true. If P is false, then P dash will be true. If P is true, then P dash will be false. If P is true, then P dash will be false. So this is your P dash. Now what is P dash plus Q? What is P dash plus Q? That will be true plus false, that is true. True plus true, that is true. False plus false, that is false. And false plus true, that is true. Now okay, this is your G1, this is your G2. Now let's make G1 by implication G2, because we want to prove that G1 by implication G2 is always true. This is what we want to prove. So let's make G1 by implication G2. This is your G1 and this is your G2. Now by the definition of by implication, what is the definition of by implication? Definition is very simple, that this G1 by implication G2, this will be true when both G1 comma G2 have same truth value. For example, here they have same truth value, both are true, so this will be true. Here they have same truth value, so this will be true. Here they have same truth value, so this will be true. Here they have same truth value, so this will be true. Now we have proven that this G1 by implication G2, this is always true. You can see here true, 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 true. There are 4 different cases that are possible. Only 4 cases are possible. And in all these 4 cases, G1 by implication G2 is true. So we have now proven that G1 by implication G2 is always true. And now actually when G1 by implication G2 is true, when this happens, that this is always true, when this happens that this is always true, then we say that G1 is equivalent to G2. So this is the definition of equivalence. So what is the definition of equivalence? Let's see. So G1 is a formula. This G1 could be any formula, okay, like any propositional logic formula you can have, and G2 is a formula. We say that G1 is equivalent to G2 if and only if G1 by implication G2 is always true. So basically, like we have shown that P implies Q, this is equivalent to P dash plus Q. This we have already shown. How did we show it? Because this is G1, this is G2, and we have shown that G1 by implication G2 is always true. This is always true. Because this is always true, so we can say that this G1 and this G2, they are equivalent. Okay, so this is the definition of equivalence. Anyway, this is how we can basically find the by implication. Okay, now this by implication is basically like this: P double implies Q. So this operation is called by implication. This is also called biconditional. Biconditional. Why this is called biconditional? Because see, in this P implies Q, this P is implying Q. Okay, this is implying Q. But in biconditional, what happens? It happens that P implies Q and Q implies P. Okay, so we can say that this P by implication Q basically says that P implies Q and Q implies P. So this is the another definition of by implication. Okay, so this is another definition of by implication. P by implication Q means P implies Q and Q implies P. So this is the definition of by implication. Okay. Anyway, we have seen all the standard operators, all the standard connectives we have seen. Now let's see some more topics, some more concepts of propositional logic. So these like these slides I will share, and you can go through these slides, or you can just take the snapshot. You can rewatch the recording on YouTube, and you can take the snapshots, and you can basically save these slides, these notes. Now let's see what is tautology, what is satisfiability. Let's see. So what is satisfiability? Basically, let's assume you consider I am giving you two formulas. For example, consider this P plus P dash. Okay, let's call it G1. So this is a formula P plus P dash. Let's take G2. This is a formula P dot P dash. And let's take G3. This is P. Okay, or you can say yeah, this is P. So now these three formulas you have, you can see all these three formulas are over a single variable. There is a single propositional variable, that is P. P is the only variable. Now let's make truth table for all these formulas. So there is only single variable, that is P. Now it can either be false or it can be true. These are the two possibilities, because there is a single propositional variable. So this either can be false or this can be true. Now what is G1? What is G1? G1 is basically P plus P dash. So first let's find what is P dash. If P is false, then P dash will be true. If P is true, then P dash will be false. So this is your P dash. Now what is P plus P dash? You can just see P plus P dash is true. P plus P dash is true, because true plus false is true. True plus false, false plus true is true. Remember, this plus is basically disjunction. P plus P dash, this is basically P disjunction P dash. Because this disjunction operator we sometimes write as plus. Sometimes we use this, sometimes we use this. So this plus basically means disjunction. That's why we call it OR. Okay. Anyway, so this is your G1, this is P plus P dash, and this is the truth table of G1. Let's see the truth table of G2. G2 is P dot P dash. What is P dot P dash? So this is P dash, this is P. So P dot P dash will be false, comma false. Now let's see the truth table of G3. G3 is P. So basically P as it is, P as it is. So this is false, comma true. Now you can notice few things. Just notice few things. If you notice G1, then you can see that this G1 is always true. Okay, this G1 is always true. So this is always true. Okay. You can notice that this G2 is always false, always false. Okay. And you can notice that this G3, this is sometimes true, sometimes false. Sometimes true and sometimes false. Okay. So this you can notice. This G3 is sometimes true, sometimes false. So what now, based on these three properties, like this formula is always true, this formula is always false, and this formula is sometimes true, sometimes false. So based on these three properties, we have different properties. Like we call this function tautology. This function is called tautology, or this formula is called tautology. So what is tautology? Tautology is a formula which is always true. Similarly, this formula G2, this is called contradiction. This is called contradiction. So what is contradiction? Contradiction is a formula which is always false. And what is this G3? This G3 is called contingency. This is called contingency. What is contingency? Contingency is a formula. Contingency is a propositional function which is sometimes true, sometimes false. What it means? It means at least one time true, at least one time false. So that is called contingency. So these are the three concepts we have: tautology, contradiction, contingency. Okay. Now, this we have something called satisfiability, satisfiable function, and unsatisfiable function. So what is satisfiable propositional logic function? What is satisfiable? Satisfiable means a formula which is either tautology, either tautology or contingency, or contingency. So, so this is the definition of satisfiable. Means a formula which is either tautology or contingency. That formula is called satisfiable. Okay. And what is unsatisfiable? Unsatisfiable basically means a formula which is contradiction. So this another name of contradiction is unsatisfiable. So this is the definition of unsatisfiable. Unsatisfiable means a formula which is contradiction. And what is contradiction? Always false. So a formula which is always false. A formula which is always false is called unsatisfiable, and a formula which is at least one time true. Okay, this tautology means always true, and this contingency means at least one time true, at least one time false. So basically, this means that at least one time true. So this satisfiable means a formula which is at least one time true. For example, this formula is this G2 is not satisfiable because we cannot make it true. We cannot satisfy it. We cannot make it true. You can see, because this is always false. But remember, we can satisfy G3. Satisfy G3 means we can make it true. Like here you can see we can make it true. Similarly, this G1 is satisfiable because we can make it true. We can make it true. So that's why satisfiable means either tautology or contingency. Unsatisfiable means contradiction. Contradiction means always false. We cannot make it true. So these are the concepts that we have. Now, few things you can notice in propositional logic. Remember, in our GATE syllabus, as I told you, we have two type of logics: propositional logic, first order logic. Two type of logic we have. So in propositional logic, what we have, this satisfiability means either tautology or contingency. Okay, and unsatisfiability means contradiction. And what is valid? Valid basically means always true. So valid means true, and true means tautology. Because what is tautology? Tautology is something that is always true, and valid means something that is always true. So valid means true, tautology true, and true means tautology. So these terminology are equivalent. These different terminology are equivalent. Okay. Similarly, invalid means not tautology. Remember, invalid means not tautology, means at least one time false. Okay, so you can say that invalid means either contradiction or contingency. So invalid means basically at least one time false, at least one time false. Means we can make it false. Invalid means we can make it false. And satisfiable means we can make it true. So that's why satisfiable means tautology or contingency. Invalid means contradiction or contingency. So these terminology, this is important. Now we have the next topic, that is predicate logic. So let's see the predicate logic. So that most of the important concepts of propositional logic we have already seen. Now we will see some concepts of first order logic. So what is this first order logic? In this first order logic, basically we have all the concepts of propositional logic. Remember, in this first order logic we have the propositional logic is already there. So basically this first order logic is a superset of a propositional logic. This is a superset. Okay, so all the concepts of propositional logic are also there. You can say that every propositional logic formula is also a first order logic formula. Okay, now some additional features we have. What are the additional features? The additional features are basically quantifiers. This is the most important additional feature that we have in first order logic. These quantifiers we do not have in propositional logic. So this is an additional feature in first order logic. Okay, and another additional feature is predicates. So these predicates in first order, in propositional logic, we don't have quantifiers, we don't have predicates. But in first order logic, we have these additional tools, these additional features, these additional concepts. Now, what is a predicate? Let's see. Predicate is basically a sentence, okay, which involves a variable and a property. Okay, for example, you can see that this px, x is even. Now you can see that this x is a variable and this is the property of x. We are saying that x is even. So this is variable and this is property of x. So that's why we can say that this px is your a predicate. This px is your predicate. Okay. Similarly, for example, a predicate can also have two variables. For example, x comma y. So you can see that x greater than y. Now this predicate has two variables, x comma y. These two variables you have. Okay, and what is the relation between these two variables? Basically we are saying that x greater than y. For example, consider this predicate. So I can say that p4 comma 3 p4 comma 3, this is true because 4 is greater than 3. So I can say that this p4 comma 3, this is true. Similarly, I can say that p3 comma 4, that is false. Okay, because 3 greater than 4, this is false. So that's why I can say p3 comma 4 is false. Okay, so this is the definition of predicate. What is a predicate? You can see, for example, this statement you can consider, this sentence you can consider, x is greater than 3. So here the variable is x. Okay, and the property is this, that x is greater than 3. This is the property. So this has two parts. The first part is variable and the second part is basically your property, or you can say your predicate. For example, this is your predicate. And finally, this complete sentence we can denote by px. So I can say that px is basically x greater than 3. This is your px. Okay, here you can see this is a predicate over one variable. You can also have predicate over two variable. You can also have predicate over three variable, or you can also have predicate over n variables. Okay, so this is the concept of predicate. Now remember that predicate over zero variable is proposition. For example, this is a predicate over one variable. Okay, here we have a variable, so this is not a proposition. But predicate over zero variable, that is a proposition. So you can say, for example, simply if I write p, and this p is basically, let's assume 2 plus 3 is equal to 5. This is my p. Here you can see there is no variable. Okay, so a predicate over zero variable, that is your direct proposition. So this is how you can see that in first order logic we have predicates, and every proposition is a predicate. Every proposition is a predicate over zero variable. Are you getting this point? So every proposition is a predicate over zero variable. So this is how you can see that this concept of predicate captures the concept of proposition. Okay, or you can say this concept of predicate is basically superset of concept of proposition. Okay, now let's see what are additional things that we have in first order logic. In first order logic, we have something called quantifiers. So this is the most important, you can say, addition. This is the most important feature of first order logic. Mainly, we study two type of quantifiers, even though there are many more quantifiers. Okay, but mainly we study two type of quantifiers. One is for all quantifier, another is there exist quantifier. This is basically your for all quantifier, and this is your there exist quantifier. This basically, and remember, in first order logic, we always, every variable has some universe. What is universe? Universe means set of values that can be taken by that variable. For example, let's assume that px, x is greater than 3. Here, the domain, the universe, or this universe is also called domain. So you can say that what is domain of x? Like, for example, the domain of x can be set of natural number. So domain of a variable means set of values that can be taken by this variable. Okay, for example, this variable x can have universe set of natural number. So this x can take any natural number. Okay, similarly, for example, this p, let's assume this qx is x is male. Okay, now here you can see the domain of this x, this could be set of all people in the world, set of all people in the world. So this is your set of all people. So this is the universe. Basically, this x can take any value from this domain. Okay, so this is your set of all people in the world. So this is how you can see that in first order logic, every variable has a domain, every variable has a universe, and that universe is basically the set of values that can be taken by that variable. Okay, now when we say that, what is this for all quantifier? This for all quantifier basically says that, for example, consider this for all x px. Now this for all x px says that for all values of x in the domain of x, let's assume the domain of x is this set of natural number. So this for all quantifier says that for all values of x in the domain of x, this px must be true. Okay, this px means for all of these values, for all of these values, and this is basically your domain of x, this is universe of x. For all these values, px should be true. For all these values, px should be true. Now what is for all, what is the there exist quantifier? This there exist quantifier basically says that for at least one value of x in the domain of x, for at least one value, for at least one value of x in the domain of x, this px should be true. Okay, so basically this there exist quantifier basically only is interested in existence. This there exist quantifier wants existence of element, means at least one element should be there. Okay, which for which this px is true. And this for all quantifier basically wants all elements to satisfy px. This for all quantifier says that for every element in the domain of x, this px should be true. So these are the quantifiers that we have. Okay, now we have something called nested quantifier. What is nested quantifier? Nested quantifier. For example, we can have this type of quantifier like for all x, for all y, p x comma y. Now here we have two quantifiers, for all x, for all y. So this is called nested quantifier. Okay, we can have like what first let's see this nested quantifier. What it is saying? It is basically saying that let's assume the domain of x is d. This is the domain of x. Let's assume, for example, a comma b comma c. So this is let's only take a comma b. Okay, so this is the domain of x. Let's assume only two values are there in the domain of x, and let's assume the domain of y is d dash, and in this we have 1 comma 2. Remember, different variables can have different domain. They can have same domain, they can have different domain. This will be given to you in the question. If they do not give you in the question what is the domain of these variables, then you should consider like both the cases. You should consider like what will happen if the domain are same, what will happen if the domain are different. Okay, so all the cases you must consider. Anyway, so let's assume the domain of x is a comma b and the domain of y is 1 comma 2. So what is this for all x, for all y? This is basically saying that for every value here, means for a, for b, whatever value you take, let's take a. So he is saying that for every value here, let's take a. Here every value means for a you can take, you should take every value here, means with a you should take 1, with a you should take 2. Similarly with b you should take 1 and with b you should take 2. Okay, this is like this because this is basically for all, for all, for every value here, for every value here, means all the possible pairs. Because here you have two values a comma b, here you have two values 1 comma 2. So how many pairs are possible? These many pairs. So for all these pairs, pxy should be true. Pxy should be true for all these pairs, for this pair, for this pair, for this pair, for this pair. So this is the definition of nested quantifier. For example, you can take one example. Consider this example. Let's assume the domain of x comma y this is the domain of x comma y. This is set of natural number, and this is 1 2 3 and so on. So this is the set of natural number, and let's assume that this pxy is given to you, that x plus y is even. X plus y is even. Now tell me what will be the truth value of this. Let's assume this is your s. Tell me the truth value of s. Tell me what will be the truth value of s. Try this. So the answer will be basically, what will be the answer? So the answer will be false, because see, this is for all x for all y. So this is saying that for all pairs, for all possible pairs, this pxy should be true for all possible pairs. Okay, but you can see that if you take this pair, consider this pair 1 comma 2, you can see this 1 is in the domain of x, because the domain of x comma y is set of natural number. Okay, so this 1 is in the domain of x, this 2 is in the domain of y. So for this pair also this pxy should be true. But for this pair you can see, that this pxy is not true. 1 plus 2, that is 3, and 3 is not even. So that's why you can say that for this pair, for at least one pair, this pxy is not true. And hence you can say that, this s is false. Okay, is this point clear? Anyone has any doubt in this? So this is how you can see for every pair, basically this for all x for all y, this says that for every possible pair this pxy should be true. But for this pair you can, for at least we have found at least one pair. Okay, and for this pair this s is false. Hence you can say that this s is false. So for at least this pair this pxy is false, hence you can say that this s is false. Okay, now let's see the next nested quantifier. The next nested quantifier is there exists x, there exists y pxy. What is this? This basically says that, let's assume the domain of x is a comma b and the domain of y is 1 comma 2. Let's assume. Then this is basically saying that there exists an element here. There exists. Let's assume this a is that element. So there exists an element here. Okay, let's assume that element is a. Now he's saying that there exists an element here, means let's assume that element is 2. So basically a comma 2. For this pair pxy should be true. So you can say that for at least one pair, this pxy should be true. This is the meaning of this nested quantifier. Okay, there exists x, there exists y. Okay, this is the meaning that for at least one pair, this pxy should be true. Now you can take one example. The same example we can take. Let's assume domain of x comma y is set of natural number. So this is the set of natural number. This is the domain of x comma y. Let's assume pxy is x plus y is even. This is your pxy. Now tell me what will be the truth value. There exists x, there exists y, pxy. Tell me what will be the truth value of s. Tell me what will be the truth value of s. So you can see that as very easily you can see truth value of s is true. Okay, because you can see this is there exists x, there exists y, means, and we have seen that this, what is the meaning of this nested quantifier? The meaning of this nested quantifier is that for at least one pair this pxy should be true, for at least one pair. So you can take this pair, like you can take 1 comma 1, you can take this pair. Okay, You can see that for this pair, pxy is true because 1 plus 1 is even. So for this pair, you can say that p1 comma 1 is true. So for at least one pair, this pxy is true. Hence, you can say that this s is true. This is how you can understand this nested quantifier. Now let's see the next nested quantifier. That is, there exists x for all y pxy. What is the meaning of this? Very simple. Let's assume the domain of x is a comma b, the domain of y is 1 comma 2. Now this is saying that there exist there exist x, means there exists a value here. There exists a value here. Let's assume that value is b. Let's assume there exists a value, means at least one value should exist. Let's assume that value is p. Now he's saying that for all value here, means with this b you should take all the values. Okay. And so basically for these b comma 1, b comma 2, for these pairs, pxy should be true. Should be true. This should be true. So this is the meaning of this nested quantifier. Very easy. He's saying that there exists x for all y, means in the domain of x, there should exist a value. There should exist a value. There should exist a value such that you can take all the values here from the domain of y. From the domain of y, you can put all the values here. And for these pairs, pxy should be true. Okay. So this is the meaning of there exists x for all y. This is the nested quantifier. Let's take one more example. Consider this. The same example we will consider. Let's assume the domain is a set of natural number. So this is the domain. Okay. And let's assume that pxy is the same. X plus y is even. The same. Okay. Now tell me what will be the truth value of s. What will be the truth value of s? Tell me. So very easily you can find the truth value of s will be false. Okay, because see, this is there exists x for all y. It says that there should exist a value, fix some at least one fixed value here, such that you can put all the values of y here, all the values of y here. And for these pairs, pxy should be true. But actually we don't have any value. Why? For example, you put an odd value here. Let's assume you put an odd value. Let's assume this is odd. Now, when you put another even value here, then for this pair, pxy will be false. Similarly, let's assume you put even value here. Now, when you put even value here, then when you put odd value here, then again pxy will become false. So that's why you can say that this pxy basically, this is not true for these pairs. Like we don't have value of x. We don't have at least one value of x such that you can put all the values of y, and for these pairs pxy should be true. We don't have any such x. So that's why you can say the truth value of s is false. Okay. So this was our third nested quantifier. Let's see the next nested quantifier, that is for all x there exists y pxy. Let's see this. This is tricky. What it is saying? It is saying that let's assume the domain of x comma y is a comma b and the domain of y is 1 comma 2. What it is saying? It is saying that for all x, means for every value here, for example, let's take a. Now he's saying that for this a there exists a y. For this a there exists a y. Similarly, but remember this is for all, means for all values. So for b also, He's saying that for B also there exists a Y. Remember, for B also there exists a Y, so this could happen. So this is what he's saying. So basically he's saying that for all value here, there exists a value here. But remember, they could have different value, they could have same value. For example, this could also happen. Let's assume this is the domain of X. Let's assume this is the domain of X, domain of X. And let's assume this is the domain of Y, 1, 2, 3. Now, this is also, like, this could also happen. Because for every value, for everyone you have someone. So this is also possibility. But remember, this is also possibility. Like, this is also possibility. Like, for everyone you have someone, for everyone you have someone, for everyone you have someone. So this is also a possibility. So what we want to say, basically we want to say that for everyone you have someone. Everyone should have someone. That is the point. Okay, everyone should have someone. That is the point. Now let's take example. So consider this. Let's assume the domain of X and Y. This is set of natural number. Both X comma Y have same domain. And let's assume Pxy is X plus Y greater than 2. This is your X plus Y greater than 2. Tell me what will be the value of, for all X there exists Y, Pxy. What will be the truth value of this? Tell me. So what will be the truth value of this? So very easily you can see the truth value of this is true, because for everyone you have someone. For example, for 1 you have 3. For example, for 2 you have 4. For example, for 3 you have 3. For 4 you have 4. For 5 you have 5. For everyone you have someone. For everyone you have someone. Everyone has someone. So that's why this is true. Okay, let's assume this is S1. For this same example, tell me what will be the truth value of this. For the same example, tell me the truth value of S2. Again, you can see that the truth value of S2 will also be true, because there exists a X. For example, you can take that X you can take as 5. There exists X. Now you can put any value here. You can put any value here. Whatever value you put 1, you put 2, you put 3, whatever value you put here. Okay, this Pxy, this will definitely satisfy. So that's why you can say that S2 is true. Okay, because you have at least one value of X, such that you can put any value here, any value of Y you can put here. The Pxy will satisfy for these pairs. Let's assume S3, and this S3 is there exists X, there exists X, there exists Y, Pxy. Tell me what will be the truth value of this. There exists X, there exists Y, Pxy. What will be the truth value of this? The truth value of S3. Very easily you can find the truth value of S3 is also true, because he is saying that for at least one pair, for example, you can consider this pair 10, 10. You can consider this pair. Okay. For this pair, you can see that Pxy is true. So we want at least one pair. We want at least one pair. So this pair we have. And that's why for this pair, you can see Pxy is true. So S3 is also true. Let's assume S4 is for all X, for all Y, Pxy. This is S4. Tell me what is the truth value of S4. truth value of S4. So very easily you can see that answer will be false. This will be false. Because here he is saying that for all pair, pxy should be true. For all possible pair. For every pair, pxy should be true. But you can take this pair. Consider this pair, 1, 1. Consider this pair. For this pair, 1, 1, you can see that pxy is not true. Okay. So we have at least one pair we have for which pxy is not true. So we can say that S4 is false. So this is how you can work out all the nested quantifier. If anyone has any doubt, then you can ask. I hope that you got nested quantifiers. Nested quantifiers are very important. Okay. So hopefully you got what is nested quantifier. Now we will see some model based questions. In GATE exam, in NATE exam. So in GATE exam, two times they have asked model based questions. Two times. These model based questions they have asked. Okay. In NATE exam for computer science, almost 4 to 6 times, almost these many times, they have asked model based questions. So these model based questions are, you can say, important from the NATE point of view, but in the GATE exam also they are asking. In 2018, recently, 2 years ago, in 2018, they have asked a question, model based question, 2 mark question they have asked. Okay. So now we will try to understand, because many students actually do not understand these questions. Many students have doubt in these type of questions. So we will cover it. Let's see. So first of all, we will, okay, remember this, what is this model? What is this interpretation? These two things we need to see. So these two concepts we need to see. What is model? What is interpretation? These two concepts we need to see. First, we will see these concepts from propositional logic point of view. Then we will see these concepts from first order logic point of view, because we have two different type of logics. This propositional logic is very easy to understand. So that's why we are taking propositional logic first. We will understand these concepts from propositional logic point of view first. Let's see. And after that, once we understand this, then we will try to understand these concepts from first order logic point of view. Let's see from propositional logic point of view. Let's see. So consider any statement. For example, consider this: P plus P implies Q. Consider this: P plus P implies Q. Okay. Now, let's make truth table for this. Let's make it. So very easily you can make the truth table. For example, this is 0 0. Remember, okay, before I tell you these things, let me tell you the similarities between Boolean algebra and propositional logic. I told you one thing in the beginning of the class. I told you that this propositional logic, this is very similar to, this is isomorphic to Boolean algebra. This Boolean algebra you will study in computer organization. Also, you will study in digital logic. In these subjects, you study this concept, Boolean algebra. Okay, 0, 1, bits and many things, voltages. Okay, so anyway, in digital logic, you will study this. Okay, and in discrete mathematics, we study propositional logic. These are isomorphic. This is also algebra. This is also algebra. Both algebra are isomorphic. Okay, both these concepts, both these topics, both these chapters are isomorphic. Let's see how. So see, here we have propositional variables, p, q, r. These are the propositional variables. And here we have Boolean variables, a, b, c. These are the Boolean variables. Okay, so this is the first similarity. Here we have propositional variables, here we have Boolean variable. You can see that each propositional variable is either true or it is false. Okay, and here you can see that each Boolean variable is either 0 or 1. So you can see each propositional variable also can take one of these two values, either true or false. Boolean variable also can take one of these two values, either 0 or 1. The next similarity is basically this true. In propositional logic we use true. In similar to in Boolean algebra we use 1. In propositional logic we use false. In Boolean algebra we use 0. Okay, so like here we are using true comma false, there we use 1 comma 0. So this true corresponds to 1 and this false corresponds to 0. Okay, now what are more similarities? More similarities you can see here. We have negation operator. So this is called negation. This is called negation. In propositional logic we call it negation. In Boolean algebra we have complement. For example, we have negation p, and in Boolean algebra we have a bar, or you can say p bar, or you can say p dash, or you can say p bar. There we call it complement. This is the word that we use in Boolean algebra, complement. And in propositional logic we use this word negation. But actually they are very similar, you can see. Okay, so now let's see next. Like in propositional logic we have conjunction. We have conjunction. Okay, for example, we have p and q, p conjunction q. In Boolean algebra we have and. We have and. For example, p dot q. There we have p dot q, or we can directly write it pq. So there we call it and, here we call it conjunction. Okay, now what are more similarities? Let me write down all the similarities that are there in propositional logic. So these are your propositional logic and these are your Boolean algebra. So what is the next similarity? Here we have disjunction. Disjunction, basically, for example, p disjunction q. In Boolean algebra, corresponding to disjunction we have or. We have or. For example, we have a or b. There we use this symbol plus, a or b. Now similarly here we have XOR, there also we have XOR. Here we have by implication and there we have XOR. Remember, this XOR corresponds to by implication. For example, there we have a XOR b. Okay, and here we have p by implication q. So this by implication corresponds to XOR. Okay, now here we have something called, for example, here we have NAND, there we have NAND. Okay, here we have NOR, there we have NOR. So this is the symbol for NAND, p NAND q. What is p NAND q? This is very easy. Basically this is negation of AND. What is NAND? NAND is basically negation of AND. This is very simple. Negation of AND. First you do AND, then you do negation. So NAND is basically negation of AND. It's like a dot b bar. Okay, so this is how you can find. And what is NOR? This is NOR. NOR means negation of OR. NOR means negation of OR. Means first you do OR, then you do negation. Here we have basically, here what we can do like this. NOR, p NOR q, basically that means p disjunction q negation. So this is how you can see. So here we have NOR, here you have NOR, here you have NAND, here you have NAND. Okay, now more similarities you can see. For example, here we have in propositional logic we have, and in Boolean algebra. In Boolean algebra, sorry, in propositional logic we have something called CNF, conjunctive normal form. Conjunctive normal form. Okay, this is what we have in propositional logic, conjunctive normal form. Corresponding to CNF, in Boolean algebra we have product of sum, POS. POS means product of sum. Okay, similarly in propositional logic we have DNF. What is DNF? That is disjunctive normal form. Disjunctive normal form. Corresponding to this concept, in Boolean algebra we have SOP, means sum of product. So these are the similarities. For example, in Boolean algebra we study POS, SOP. Many times we write SOP expression. Okay, we write K-map, and from the K-map we write SOP expression, or we can write POS expression. product of sum of product. So once you know product of sum very easily, that is exactly equal to CNF. So this product of sum is same as CNF. Similarly, this sum of product is same as DNF. Okay. So once you know this concept, you already know this concept. You don't have to worry about this concept because DNF is same as SOP and POS is same as CNF. These are the similarities between propositional logic and Boolean algebra. Once you know one chapter, if you know Boolean algebra, if you are master of Boolean algebra, then automatically you are master of propositional logic. Similarly, if you are master of propositional logic, then automatically you are master of Boolean algebra. For every concept that we have here, we have a corresponding concept here. For every concept that we have here, we have a corresponding concept here. Okay. Okay. So these are the things. Now, so I was talking about these. So this is your, okay, this is your propositional logic function, or you can say this is your propositional logic formula. Okay, let's call it G1. So this is your formula. P disjunction, this plus is basically disjunction, P implies Q. Okay, so what are the different possibilities? I told you 0 means false, so instead of writing false comma false, I am writing 0 comma 0. So what are the different possibilities? Either 0 comma 0 or 0 comma 1 or 1 comma 0 or 1 comma 1. These are the different possibilities. Now let's make the truth table for this G1. So first let's make the truth table for P implication Q. This you already know. P implication Q is this. This is P implication Q. Okay. Now what is P plus P implication Q? So this is your P implication Q. This is your P. Now you do their disjunction. So 0 plus 1 that is 1, 0 plus 1 that is 1, 1 plus 0 that is 1, and 1 plus 1 that is 1. You can notice that all ones we have here. Okay. Now let's create another function also. P dot P implies Q. Let's consider this also. P dot P implies Q. This is your P implies Q. This is your P. Let's find. So 0 dot 1. So let's call it G2. Let's call it G2. So this G2, this is your G1. And what is your G2? G2 is P dot P implies Q. This is your G2. Okay. So what is G2? G2 is basically P dot P implies Q. That will be 0, 0, 0, 1. This is your G2. Okay. Now, what I want to say, now let's see the concept of interpretation. First of all, what is interpretation? Now, in propositional logic, okay, okay, actually the concept of interpretation, we need to see the concept of interpretation and this concept of model. Most of the time we use these concepts in first order logic, most of the time. Okay, this interpretation concept and model concept, these concepts we use in first order logic, but we can use these concepts in propositional logic also, because every propositional logic is also first order logic. Propositional logic is subset of first order logic. So in propositional logic also we can use it. In first order logic also we can use it. In first order logic, every variable, whatever variable you have, that variable has a domain. And that domain can have, for example, set of natural number, set of all people. That domain can be anything. So that is the difference here. Like in first order logic, the domain of a variable can be anything, whatever you want, like whatever you need. Okay, whatever relevant domain you want, that you can take. So the domain of X can contain any number of elements, okay, whatever you want. But in propositional logic, what variables we have? In propositional logic, we have variables which are propositional variables, like P, Q. These are the propositional variables, and the domain of propositional variable is only true comma false. So the domain of propositional variable is only true comma false, nothing else is there. So this is the domain of propositional variable in propositional logic. But in first order logic, the domain of a variable could be anything. So this is the first difference. So this you can note that in propositional logic, the domain of a propositional variable that is only true comma false. So this propositional variable either can take true or it can take false. These one of these two values it can take. Okay. Now, what is interpretation? So this is the concept of universe, or you can say this is the concept of domain or universe. Now let's see the concept of interpretation. And what is interpretation? Interpretation is basically what information you need, what information you need to to deduce the truth value of a function, to deduce the truth value of a formula. For example, if I ask you, let's assume, consider this. If I ask you what is the truth value of p plus q, tell me, can you answer it? What is the truth value of p plus q? Tell me. Can you answer it? Can you answer this question? Think about it. Can you answer this question? I'm directly asking you, what is the truth value of p plus q? You cannot answer this question. You need some additional information. What information you need? The information that you need is this. Like, what is the truth value of p and what is the truth value of q? For example, truth, if I give you truth value of p is true and truth value of q is false, if I give you this, now if I ask you what is the truth value of p plus q, now you can answer. Now very easily you can answer. With this information, you can answer this question very easily. So this is called interpretation. So the very simple definition, if I want to say, okay, without any formal terminology, without making it hard, the simple definition, if I want to say, then what is the definition of interpretation? Definition is very simple. All the information that I need to find out the truth value of a propositional formula, that is interpretation. Okay, so for example, this is one possible interpretation. Another possible interpretation is this: p is true, q is true. This is another possible interpretation. Another possible interpretation is p is false, q is false. This is another possible interpretation. Another possible interpretation is p is false, q is true. So these are the interpretations that are possible. Okay, these four interpretations are there. So how many interpretations are there for this formula? For this formula, you have four interpretations, because you only need, if I give you this interpretation, then you can easily find out the truth value of this formula. If I give you this interpretation, then you can easily find out the truth value of this formula. So these are called interpretations. And you can see these are your rows in the truth table if you see. So in propositional logic, the interpretation is nothing but your row in the truth table. For example, here you can see this row is an interpretation for this formula, for this formula. For G1, if I want to ask for G1, then for this G1, this row is an interpretation. This row is an interpretation, this row is another interpretation, and this row is another interpretation. So how many interpretation I have? Total 4 interpretation I have. Okay, total 4 interpretation. Let's call it I1, I2, I3, I4. Total how many interpretation I have? Total 4 interpretation I have. So this is the definition of interpretation in propositional logic. Very simple definition, I think. Okay, the definition is very simple. Basically, interpretation is nothing but the truth value, the truth combination, the truth assignment to each propositional variable in the formula. If I'm talking about G1, then what I need the truth assignment of p comma q. So I have 4 rows, hence I have 4 interpretation. Now what is the definition of model? Now we will see the definition of model. So we have seen, from the propositional logic point of view, we have seen the definition of interpretation. From the first order logic point of view, the definition of interpretation is still pending. This we will see. But first, let's see the definition of model from the propositional logic point of view. What is the definition of model? Model is basically an interpretation for which our formula is true. So you can say an interpretation, an interpretation for which our formula is true. Interpretation which makes our formula true. That interpretation is model. Okay. So again, coming back to here in this example, you can see that if you consider this G1, then for this G1 we have four interpretation, and each interpretation is a model, because in each interpretation this G1 is becoming true. So each interpretation is a model. Is it clear? Similarly, if I talk about G2, in G2 there is only one model. This is the only model I have, because only this interpretation makes our formula true. So what is model in propositional logic? In propositional logic, model is an interpretation which makes our formula true. Hence, for G2, you have one interpretation, sorry, one model. Total four interpretation you have, but model is only one. For G1, you have four interpretation, and each interpretation is a model. Okay, so this is how you can find how many interpretation are there, how many model are there for a propositional logic formula. Remember, right now we are only talking about propositional logic definitions. So we have seen the definition of interpretation in propositional logic. We have also seen the definition of model in propositional logic. What are the remaining things? Remaining things are the definition of interpretation in first order logic, the definition of interpretation in the definition of model in first order logic. These two things are remaining. But before we see these two things, let's do some practice of propositional logic. Let's do some practice. Consider this question. This is a NET exam question. Let me tell you. This is a NET exam question. Tell me what will be the answer for this question. Try this. Take a copy, take a pen. Try to solve this question. He is asking, consider four propositions. A, B, C, D. These are four propositions. He is asking how many models are there for the following sentence. For this formula, let's call it G1. Let's call it formula G1. For this formula, he is asking how many models are there. Take a copy, take a pen, try this question. Anyone want to answer? Let's solve it. Let me solve it. See, what is this formula? This formula is basically negation A or negation B or negation C or negation D. This is our formula. First, okay, we can easily convert it. Actually, this is your De Morgan law. They have applied De Morgan law. Basically, we can write like this: A and B and C and D whole negation. This same thing I can write like this, because this is De Morgan formula. What is De Morgan formula? Let's see. The De Morgan formula is like this: P and Q bar. This is nothing but what you do. You do negation of P, you do negation of Q, and you convert conjunction into disjunction. You convert disjunction into conjunction. You complement each variable. P dash will become P, Q will become Q dash, Q dash will become Q. So basically you complement each variable, you negate each propositional variable, you convert this conjunction into disjunction, you convert disjunction into negation, disjunction into conjunction. So this is how you can apply the De Morgan formula. So finally you will get this. This is your De Morgan formula. Similarly, P disjunction Q negation. What is this? This is nothing but P dash conjunction Q dash. Okay, so this is your De Morgan formula. You can apply it. Now what we got? So this given formula is nothing but ABCD bar. This is basically your ABCD bar. Now he is asking these four variables you have, and he is asking how many models. First, let's find how many interpretations are there. How many interpretations are there? Very easy, you can find. In propositional logic, each interpretation is a row in the truth table. So in the truth table, how many rows you have? For four variables, how many rows you have in the truth table? You have 2 power 4 rows in the truth table. And each row is a interpretation. So how many interpretations you have? Total 16 interpretations we have. Because remember, what is interpretation? Interpretation is the truth assignment to each variable. Okay, and each variable can have two possibilities, either true or false. Each variable has two possibilities. So how many total possibilities you have? You have 2 power 4 possibilities. So in your truth table, you will have 16 rows. Hence you have 16 interpretations. Okay, total 16 interpretations you have. So if he is asking number of interpretations, then that will be 16. Number of interpretations will be 16. But he is asking number of model. What is a model? Model is an interpretation which makes our formula true. So let's see what will make our formula true. Tell me what will make our formula true. Which interpretation will make our formula true? You can notice that if you want this G1 to be, let's call it G1. If you want G1 to be true, then basically you want ABCD to be false. You want this to be false. When this becomes false, okay, then G1 will become true. And we want G1 to become true. Okay, so the number of interpretations which will make G1 true, that is nothing but number of interpretations which will make ABCD false. Now how many interpretations will make ABCD false? Total 15 interpretations will make ABCD false, because the only interpretation that will make ABCD true, that is your A equal to B equal to C equal to D is equal to true. This is the only interpretation which will make ABCD true. All other interpretations will make ABCD false. So all other interpretations, these 15 interpretations, will make ABCD false. Hence, this ABCD complement will become true. Okay, and this is what we want. So number of models will be 15, because 15 interpretations are there which will make our formula true. So the answer will be 15. These many models we have. Is this clear? Anyone has any doubt? Let me know if anyone has any doubt. Because first, once we understand this definition of interpretation, definition of model from the propositional logic point of view, then very easily we can understand the definition of interpretation, definition of model from the first order logic point of view. In GATE exam, 2 times they have asked question on models from the first order logic point of view. Okay, so first you should understand the definition from the propositional logic point of view. Now this is also NET question. Total you have 3 questions you have. All these are NET questions. Okay, so let me solve one of them, and you can try other 2 as a homework. You can take other 2 questions as a homework. Let me solve this question A. So what is this question A? This is your A conjunction B disjunction C conjunction D. Okay, this is your formula. Now he is asking, basically he is asking that four propositions you have A, B, C, D. These are 4 propositions, and he is asking how many models are there. Number of models he is asking. First, let's find the number of interpretations. Number of interpretations is very easily we can find, because we have four propositions. So number of interpretation will be 16. Because in propositional logic, interpretation is nothing but a row in your truth table. For example, this is your truth table. In this truth table, you can see that this row is a interpretation. Every row is an interpretation. What is interpretation? Interpretation is basically truth assignment to each propositional variable. Okay, so each row is a truth assignment to each variable, each row. So the number of rows is equal to number of interpretations. So the number of interpretations will be same for here also, for this A also 16, for this B also 16, for this C also 16. Like, don't make this mistake. Some students make this mistake. What they do, A or B, they think that the number of interpretations will be 4, because they think that there are only two variables, so the number of rows will be 4. No, remember, the number of propositions are given to you. Total 4 propositions you have, A, B, C, D. And with these 4 propositions, you can have this function also. With these 4 propositions A, B, C, D, you can also make this function, this formula also you can make. So remember, when you have 4 propositions, then number of interpretation will be 16. So whatever question you take, whether you take this question, you take this question, or you take this question, the answer, number of interpretation will be 16, because number of propositional variable, that is nothing but 4. So this is how you can find the number of interpretation. Now let's find the number of models. What is a model? Model is an interpretation which makes our formula true. So we want our formula true. So this is a disjunction, you can see. What I am going to do, I am going to find number of interpretations which will make our formula true. And to do that, I am going to find how many interpretations will make my formula false. Let's see. If I want to make this formula false, then what will I have to do? I will have to make this false. I will have to make this false. So basically this AB should be false, and this CD should be false. Okay. Now, how many ways are there to make this false? There are total 3 ways to make this false. Okay, either A can be false, or B can be false, or both can be false. So there are 3 ways to make AB false. Similarly, there are 3 ways to make CD false. Together, how many ways are there to make this false? That will be 9. So total 9 ways are there to make this formula false. But we want number of models. And what is a model? Model is an interpretation which will make our formula true. So total 9 interpretations are there which will make our formula false. So 16 minus 9, 7 interpretations will make our formula true. So we have 7 models. For this question, we have total 7 models. Okay, for this question A, total 7 models will be there. Answer will be this. Okay, and actually you can see this also. I have made this truth table also. From the truth table also you can understand. For this option A, this is the truth table that you will get. Okay, and in this truth table you can see total number of interpretation is 16, number of rows is 16, so number of interpretation is 16. But number of models is, this is model, 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 this is model. So number of model is 7, because for these 7 interpretations, okay, for these 7 interpretations, you can see the formula is becoming true. So total 7 models are there. You can solve this question, you can solve this question, you can try this as a homework, you can take it. Okay, so now actually the next topic that I want to discuss, okay, let's similarly actually you can take, this is also a net question. Okay, you can very easily you can solve it. Let me solve this question. Total 4 propositions you have, A, B, C, D. Total 4 propositions. He is asking how many models are there for this formula B or C. So remember, total 4 propositions are there. So number of interpretation is fixed. Number of interpretation will be 16. What will be the number of models? Tell me, what will be the number of models? You can try this. Take 2 minutes and try this question. How many models will be there? Anyone got the answer? So anyway, let's see. So the number of interpretation will be 16. Now let's find the number of model. What is model? Model is a interpretation which will make this true, B or C. This should be true. So let's see how can we make it true. So see, remember here only we have two variables. So we are free to choose any a comma d. This a comma d is free. Okay. So we want to make this true. So how many possibilities are there? Total 3 possibilities are there to make this true. B comma C. Total 3 possibilities are there. But remember, these are free. So for them you have total 4 possibility. So total 12 possibility are there. Total 12 interpretations are there, which will make our formula true. So the answer will be 12. Okay. Remember, answer won't be 3. Like some students, what mistake they do? They make this mistake. They just look at these two variables, this variable, this variable. They just look at these two variable and they say that total 3 models are there. No, there are 12 models. Why? Because we have total 4 propositions. So a comma d is also there. It's like this. Let me tell you, it's like this. When you make the truth table, it will be like this: A, B, C, D, and then you will have 0, 0, 0, and total 16 rows will be there. And finally, for example, in this row, this B or C will be false because B is false, C is false. For example, in this row, this will be true. For in this row, this will be true. Okay. In this row, this will be true, and so on. So you can see that, for example, in this row, this will be true, and so on. So total 12 models are there. So this is how you can very easily solve it. Okay. Hopefully this model concept from the propositional logic point of view, this model concept is clear. I hope that. And from the first order logic point of view, this concept is remaining. So we need almost half an hour. So we will see it in the next lecture. So from the first order logic point of view, this interpretation, this model, these concepts we will see in the next lecture. But let me take that question. I told you, I gave you one claim in the beginning of the lecture, and I told you that I will prove it at the end. So this was the statement I was talking about. A claim I have given a claim, and that claim was this. There, this is called drinker paradox actually. Okay, so there exists a person, there exists a person in the world, there exists a person in the world such that if he or she is a drinker, is a drinker. By drinker I mean alcoholic, not the water drinker. Okay, anyway, so there exists a person in the world such that if he or she is drinker, then everyone is drinker. So I told you that from the common sense point of view, if you think about this question, then you will see that this is false. This statement is false. You will think like this. Okay, but actually from the discrete mathematics point of view, this is true statement. Okay, let me prove it why this is true. And you can search for it. This is called drinker paradox. On Wikipedia you can search it. This is your drinker paradox. There you can prove, there the proof is also given. But anyway, let me prove it from the mathematical logic point of view. I will prove it. Okay, so here what he's saying, what I will do, this is English statement, and I will convert this English statement into first order logic formula. So what he's saying, first of all he's saying there exists a person, means there exists X in the world. So the universe is a world. So the domain of X is set of all people in the world, set of all people in the world. This is domain of X. Okay, so basically there exists a person in the world such that so there exists a person in the world such that if he or she is drinker, this is a if then statement, remember, this is a if then statement. So he's saying if he or she is a drinker, means if X is drinker, dx implies everyone is drinker, means for all y is a drinker. Okay, and the domain of Y is also set of all people in the world, because he's saying then everyone is drinker, means for all y is a drinker. So this is the formula. What we have done, this English statement we have, and we have converted this English statement into mathematical logic formula. Okay, now all we need to do is prove that we need to prove that this formula is always true. This formula is true. We need to prove it. Let's see how to prove it. So this formula is true. This we need to prove. Let me write this formula. For all x, if dx implies for all y, dy. Okay, and the domain of x comma y, the domain of basically the, you can say the universe of x comma y, that is your set of all people in the world. Okay, so this set of all people. Now, okay, let's call it formula E. This is your formula E. Okay, now let's prove it. Now to prove this, I am going to take two cases. These two cases are possible. The case one is basically assume that everyone is drinker. Let's assume this is the case one. Everyone is drinker. Assume everyone in the world is drinker. Everyone is drinker. Now in this case, you can very easily see that in this case E is true, because everyone is drinker. So automatically what will happen? This is see, when everyone is drinker, then what will happen? This will become true, because everyone is a drinker. So this will become true for all y, for all y dy. This will become true. So this is become true. And you know that in implication, P implies Q. When this Q is true, then automatically this complete implication will become true. So this complete thing will become true. And hence, you can say that there exists X, and inside you have true. So that's why you can say that in this case, this formula E is true. This formula E is true in this case. What is another case possible? So one case is this is possible, like everyone is drinker. What is another case possible? At least one person is non-drinker. At least one person is non-drinker. One person. Let's assume that that person is B. At least one person is non-drinker. You can see that only these two cases are possible. Either this case is possible or this case is possible. Either everyone is drinker or at least one person is non-drinker. Let's assume that that person who is non-drinker, that person is B. So this B is non-drinker. He does not drink. Okay. Now, what we can see, this formula E is actually true from the B point of view, because this formula E is saying there exists X. Now take X to be B. We only want at least there exists X. So take this x to be b. This b you have, take this x to be b. Okay, now let's check. So when you do this, when you take this x to be b, then what will happen inside? What will happen? This dx, this db will become false. db implies for all y dy. You can see that when you take x equal to b, then this db, and what is db? db means b drinks, but b is a non-drinker, so this db will become false. Because this db has become false, now you can see in implication, when this p becomes false, then this complete implication will become true. So this complete thing will become true. This complete internal thing, this will become true. So this e will become true because we have, there exists x, and that x is b. So we have at least one element for which this internal thing is true. So you can say that this e is true. So in this case too also e is true. And these are the only two cases possible. Either this case is possible or this case is possible. Either everyone is drinker or at least one person is non-drinker. And in both the cases, you can see this formula E is true. So what you can say? You can say that this statement is true. This statement is actually true from the discrete mathematics point of view, from the mathematical logic point of view, from the artificial logic point, artificial intelligence, because in the artificial intelligence, actually, we use propositional logic and first order logic. Okay, when you will study artificial intelligence, at that time, first you will have to study first order logic, propositional logic, interpretation model, all these concepts you will have to study. Then you will start studying artificial intelligence. So you can say that from computer point of view, from artificial intelligence point of view, from mathematics point of view, this statement is true. From the common sense point of view, clearly this statement is not true. But anyway, this is the point. In GATE exam, if they ask you this type of question, don't just directly use your intuition, don't use your common sense, because you can see that mathematics does not run on common sense. Mathematics runs on concepts. So this is how you can prove that this claim is true. Okay. So this is called drinker paradox. You can search it on internet, you can search it. Okay. This is your drinker paradox. Anyway, now let me tell you, actually, these type of puzzles, this drinker paradox that we have seen, this is one type of puzzle. Like if you go and you tell anyone this statement, then they will tell you that this is false because they don't know discrete mathematics. But you know that mathematically this claim is true. So these are mathematical puzzles. These all are called mathematical puzzles. So these are nice things. Okay, you should solve these things like mathematical puzzles. These are very nice. You will use your brain. Okay, and to solve these type of mathematical puzzles, you can there is a book, and that the name of that book is, what is the name of this book? What is the name of this book? So this is the name of the book. Okay, so you can see the name of the book is, what is the name of this book? Okay, and this is the book name, and this is by some Raymond Samuel. Okay, so he was a you can say one of the you can say greatest mathematician, logician basically. He used to write logical puzzles, like mathematical puzzles. So he knows discrete mathematics, he knows propositional logic, first order logic, second order logic. So this logic, he knows mathematical logic, and he has written this book. In this book, you will find many mathematical puzzles, like this puzzle that this drinker paradox I found. First, I found in this book. Then I searched on internet and I found Wikipedia page also. But actually, these type of puzzles you will find in this book. So after GATE exam is over, don't do it right now. But after GATE exam is over, and if you are interested in these type of mathematical puzzles, where you need to use mathematics, okay, you need to use mathematics to solve these questions. So you can try these things. You can try to study this book after your GATE exam is over. Once you go to IIT, IISc, at that time you can if you want, then you can read this book. Anyway, So the session is almost, the time is over, and some things are remaining. Like I wanted to cover the first order, this model based concepts, the model based questions from the first order logic point of view. I wanted to cover, like in the slides I have these things. Okay, for example, you can see I wanted to cover these questions, all these questions I wanted to cover. This is your gate 2018 question. If you see, this is gate 2018 question. So anyway, we will cover these concepts. The remaining concepts we will cover in the next class. So let me know if you have any doubt. Else, we will meet in the next session. If anyone has any doubt, then you can ask. Hopefully, you got something, you understood something in today's class, something new. I hope. And still, if anyone has any doubt, then you can ask. Anyone? Any doubt? Okay, no doubt, I think. No one is asking anything. So, see you in the next class if no one has any doubt. In the next class, we will see these model based questions. Okay, these model based questions we will see from the first order logic point of view. Already from the propositional logic point of view, we have already seen almost half an hour or maybe 45 minutes we need. And then we will start new topics like graph theory. We will start graph theory in the next session. Okay. Okay, everyone. Thank you. Good night.